Hello, we will continue with the section 5 in chapter 5, that is the second law and heat pump cycle. I'm not going to spend too much time here because we have covered the power cycles and the refrigeration cycles and their relation with the second law in the previous videos. And this is heat pump cycle. Its schematic is the same as the refrigeration cycle. So we have the hot reservoir, we have the cold reservoir, we put the heat pump cycle as such. It receives heat from the cold reservoir at Tc and rejects heat to the hot reservoir at Th while consuming the power. And this is the cycle. It is exactly the same, but here the idea or the objective is this one. Because it's a heat pump cycle, the objective is heating and to make this Th hot. Okay? Therefore, it is similar to refrigeration cycle, but here in the heat pump cycle, the objective is to provide heating instead of Q.C. In the refrigeration cycle, the objective is Q.C. In the heat pump cycle, the objective is Q.H. Okay? Therefore, the coefficient of performance for the heat pump cycle, which we use gamma for that one, is Q.H over the power of the cycle, which is the net power. Again, I'm not going to do this over here. What is the maximum possible coefficient of performance that a heat pump cycle can get is it's going to be 1 over 1 minus Tc over Th. Okay? So in order to get this one, okay, you have to use the entropy generation term to be equal to 0. Again, the work cycle over here is going to be Q.H minus Q.C. Okay, and using the entropy balance, write down Q.C in terms of Q.H, plug it into here, you will get and equate entropy generation term to be 0. You are going to get this. That's basically all that you can do about the or to get the maximum coefficient of performance for the heat pump cycle. Okay. So let's move to the next section. In the next section, we talk about the ideal processes in this chapter, right? So in this section 6, there is a special cycle that's called the Carnot cycle. So it is an ideal cycle with the following processes. So ideal cycle means when you want to calculate the efficiency of a power cycle, refrigeration cycle, or a heat pump cycle, it doesn't matter which type of the cycle, you are comparing the efficiency or coefficient of performance with the Carnot efficiency or Carnot coefficient of performance, because that's an ideal cycle. All the processes are ideal. So let me write down what kind of processes we have in the Carnot cycle. It consists of 4 processes. And what happens to the temperature, heat transfer, entropy generation term, and entropy itself. The entropy part will come in chapter 6, but I will write it here just to give you the idea. The first process is adiabatic compression. Okay. So since it is given as adiabatic, okay, by definition heat transfer is 0 and entropy generation is also 0 because it's an ideal process. Okay. And later on we will see if you have adiabatic and entropy generation 0, which means reversible process. Reversible and adiabatic is going to make it isentropic process. Isentropic means constant entropy process. That will come in chapter 6. Okay, so this one, I'm writing it here, but we will study that actually in chapter 6. Constant entropy process is called isentropic process. The second process is isothermal expansion. It is isothermal, therefore dT is equal to 0, change in temperature is 0, it's isothermal, and by definition, since it is ideal, entropy generation is 0. Okay? And process 3 to 4 is adiabatic expansion. So in the expansion, as you might remember, volume increases, in compression volume decreases. This is adiabatic, therefore heat transfer is 0. And since it is a perfect cycle, entropy generation is 0. There is no losses, there is no irreversibility. Okay? And this is going to be isentropic process as well. And finally, last process is going to be isothermal compression that you might. It is isothermal, temperature change is 0. It is perfect system, therefore entropy generation is 0. Okay? So, Carnot cycle is a cycle where you have all these processes occurs at the same time. Okay? So in process, in series actually. 1 to 2, 2 to 3, 3 to 4, 4 back to 1. It's a cycle. And the Carnot cycle, if you have all these 4 processes, it gives you the maximum possible efficiency for power cycles or maximum possible coefficient of performance for the heat pump or refrigeration cycle. Carnot cycle can be, again, power cycle, it can be refrigeration cycle as well. And once again, one common mistake, let me be clear here. Isothermal does not mean it is adiabatic, as you can see. Adiabatic temperature can increase or decrease, but heat transfer is 0. Okay? In the isothermal one, temperature change is 0, but in this process, you will see that heat transfer is positive. In this one, its compression heat transfer is going to be negative, which means heat loss. Right? So it's a special process that's called the Carnot cycle. Right? And in the last section, in chapter 5, which is section 7, we have the second law statements. Actually, these are important statements. This is how the entropy balance is, or actually, before finding the entropy balance, before finding the entropy generation term, etc., people are utilizing these statements. So the first one is Clausius statement. What Clausius said back in the day was, you have the cycle, okay, and it says, since heat is from the hot body to cold body, okay, what Clausius said, you cannot have heat occur from cold body to hot body without any energy input, without any work input. So this statement simply states that, well, let me write again, TH is greater than TC. Okay? And what it says is, Q heat transfer from TC to TH, basically cold to hot, okay, with power input to be equal to 0, which is net power, okay, is impossible. This is the Clausius statement. And as I said, it might satisfy, as in the wall example that I gave you at the beginning of chapter 5, this would satisfy the first law of thermodynamics, okay? But it's going to violate the second law, okay? And before the second law, there was Clausius statement, which states heat transfer will not occur from cold body to hot body without any energy input, work input to the system. And as important as this Clausius statement, an equivalent statement actually is the Kelvin-Planck statement. And these two state, I already derived this for you, but we have TH. So these people considers a power cycle in this case, okay, and say Q dot C cannot be equal to 0. That's what they say. Okay. So again, TH is greater than TC here. And this statement says 100% conversion of Q dot H to power cycle is impossible. In other words, what they said was Q dot C cannot be equal to 0. That's what they say. You have to have Q dot C for this conversion, which I proved in the previous sections in this chapter. Okay. So that's the Kelvin-Planck statement. Again, Q dot H is equal to W dot cycle is going to satisfy the first law of thermodynamics, but theoretically it's impossible. Okay, and these days we utilize entropy balance or second law of thermodynamics to prove that this is impossible, which I did. And finally, Clausius inequality. So we have the Clausius statement right over here. And if you apply that idea to a cycle, the Clausius inequality is for the cycle. So if you take the cyclic integral of all the heat transfers in a cycle with their corresponding boundary temperatures, okay, so TB, B stands for boundary, it is less than or equal to 0. Okay, so this is referred as the Clausius inequality. Again, at that time there was no entropy balance. Historically, this is before the entropy, chronologically this is before the entropy balance or the second law. And this is what Clausius came up with, referred as the Clausius inequality. And these days, let me prove why this is as such. Consider the entropy balance. Okay. So this is cycle. Therefore, the left-hand side is equal to 0. And for the right-hand side, you are going to have these ones, right? Plus the entropy generation term. Delta entropy generation term. Okay. Therefore, since this part is always positive or equal to 0, okay, to make it 0, this is less than or equal to 0, which is Clausius stated, Clausius inequality. Okay, so from here, this is the summation for the entire terms, okay, for the entire cycle. Therefore, this is 0 because it's a cycle, right? Del Qj over Tj is less than or equal to 0. Okay, this is what Clausius stated. Right? Because entropy generation term is always positive or equal to 0. So these are important inequalities or statements that is related to the second law. Okay, so typically the discussions regarding the second law starts with these, like the Clausius statement, Kelvin-Planck statement, how they are derived, why we need them, why there is like Clausius inequality, so on and so forth. And then they come into the term called entropy, and then the entropy balance. Okay, but now that we directly have or can utilize the entropy balance, I started chapter 5 directly with the entropy balance and the property called entropy. Okay, so but know that these statements, Clausius statement, Kelvin-Planck statement, and Clausius inequality came before the entropy balance or the second law of thermodynamics. Okay, so that's kind of the end of the chapter 5. Okay, in this chapter, we introduced or we learned the need for the second law of thermodynamics, how first law lacks to say whether a process is possible or not. Therefore, we utilize second law to state whether a process is possible or not, and we find the limits of a process, of a cycle, using the second law of thermodynamics. Okay? Chapter 6 is going to be more applied. More analysis will come into chapter 6. So let me know if you have any questions. That's all for now. Take care, stay safe, bye bye.